So good afternoon, everybody, or good evening, depending on where you're watching from. So today we're gonna have a presentation here presented by Dr. Shahil Shah, which is entitled Impedance Scan Tools for Stability Analysis of IBR Grids, which is a very interesting theme and has been getting a lot of attention lately in academia and industry. So Dr. Shahil Shah is a senior engineer for grid integration at the National Renewable Energy Laboratory in Golden, CO. He received his PhD degree from Rensselaer Polytechnic Institute in Troy, NI. He has been working for the past 15 years on modeling, control, and stability of wind and PV plants, HVDC transmission systems, and power systems with high levels of inverter-based resources with specific emphasis on impedance-based methods for analyzing the stability of IBR grids, which is the topic of the webinar today. He's leading several DOA projects at the NREL on these topics, and he has led the development of first of its kind impedance measurement system for utility scale wind turbines and inverters. He is serving as an editor of the IEEE Transactions on Energy Conversion, and he recently received the ESIG Excellence Award for leadership in the design and analysis of grid-forming inverter systems. He has been actively contributing to IEEE, IEA, ESIG, and CGRAE working groups focusing on stability of power systems with high levels of inverter-based resources. So after this large resume from our guests, we thank you for your time, Dr. Shahil Shah, and I'm going to give you the word for the presentation. Just to mention here, the questions and answers, they will be at the end of the presentation, so put all your questions in the chat, please.
Thank you, Andre, for the kind introduction. Hello, everyone. Welcome to this webinar, which is on impedance scan tools for stability analysis of IBR grids. So I'm going to talk about these problems of control interactions and oscillations in grids that we are seeing more and more because of penetration of inverter-based resources or IBRs. IBR, what I mean by IBR is wind and PV plants or FACS devices, HVDC converter stations, anything which uses power electronics can be called an IBR in a way, and then they, because of fast dynamics, create these oscillations and resonance issues. I'll talk about impedance-based stability analysis method for understanding these control interactions, which are local in nature, and then how we can scale the impedance method to do system stability analysis or understand stability of power systems with large amount of renewables. Then I'll talk about NREL's impedance scan software tool, a tool that we are developing here to analyze stability of power grids with large amount of renewables and the impedance measurement system. So the reason we are looking at this tools or impedance scan tools is because of what you see on your screen. These are all the real measurements. Some people call it control interactions, oscillations, resonance. They, depending on the frequencies, sometimes we call them subsynchronous resonance, subsynchronous control interactions, or torsional interactions. But ultimately, these all are oscillations that you are seeing. They are a result of small signal instabilities or system being not able to hold steady at an operation point. They are very like the problem is can come appear in different form. For example, what you see here in Germany, that is an oscillation that occurred in I believe in 2014 between an offshore HVDC station and offshore wind power plant, which resulted in wind plant being disconnected from the grid for several months, resulting in huge financial losses. Then on the top right, there's a subsynchronous resonance or oscillations in a wind power plant in US. In China, there have been several such oscillation events which have resulted in bulk grid stability issues because of these oscillations, you lose large amount of generation from renewables as well as sometimes conventional generation. For example, here in the UK, that event which happened, I think, in 2019, August, where an offshore wind power plant rated at around 700 megawatt had oscillations, and then it tripped because of some fault in the grid, and then it created a blackout in several parts of the country. So that is the reason we need to understand these oscillations, how to eliminate them. And if you have to think in terms of like a very simple terms, these are really vibrations. If you have to give analogy with mechanical systems, when a mechanical structure is vibrating, you can see it vibrating, but these oscillations, they generally appear, there are no visual manifestation unless there is some failure of a device. So they appear in electrical quantities like active power, reactive power, voltages, and currents. What I was showing in the previous screen was more like a local interactions that happen between two subsystems, for example, between an offshore HVDC, an offshore wind plant, or between a wind plant and the grid AC network. But now we are seeing something what can be called wide area oscillations or wide area control interactions. For example, on the left side, you see these two oscillation events that have happened in Australian grid at 7 hertz and 19 hertz. In the middle, there's another oscillation event which happened, I think, last year in Scotland, and it was felt in big part of the UK grid. And on the right, there are some PSCAD studies which shows that if you want to operate uh, Hawaiian Islands in US with 100% inverter-based resources, that there are some we might see these oscillations which might be disruptive and a big concern for stability. So whenever we see these oscillations, either in field or in simulations when we are doing planning studies, the question that comes to mind is how each of these inverter-based resources are impacting the damping and frequency of these oscillation modes, or to put it simply, like which IBRs are causing these oscillations. Is it possible that if I remove some of the IBRs, then these oscillations will disappear? If I have to install some additional equipment like a dampers using Statcom or some filters, where we should install them? So we want to address that question, because when you see these oscillations, there's hardly you can do about understanding them directly, like who is causing them, because they are appearing all over the system. It's not that it's appearing only at one wind or PV plant, so or at one HVDC substation. So that is the question that we need to address, and we need a tools to do address this type of questions. Before talking about the tools, let me give an overview of like why we are seeing these oscillations or these control interactions. And the main reason is that in classical power system, when we had just synchronous generators, the dynamics were very simple. Like if you take any synchronous generator, you can very well describe its electrical dynamics through few using few differential equations, 9 to 15, and there are standard models available which very well define how the synchronous generator is going to behave. But with all the inverters, wind turbines, HVDC, their controls are complex, they are fast, they are all over the place in terms of frequency range. They are not standardized, uh, not disclosed by vendors to protect their intellectual property. So they basically add a lot of richness to the power system dynamics. And that is the reason we see more and more of these control interactions all over the world, where power systems are trying to increase the amount of renewables in their generation portfolio. So to solve them, we need to emulate what mechanical engineers have been doing for years, and that is we need to do model testing, model analysis, and damping. Uh, what mechanical engineers, they see these vibrations, what and they have similar problem. They have complex structures. They are hard to be that that are difficult to be modeled mathematically, and they also see these oscillations and want to understand what are the modes when they design a structure. So uh, you vibrate a structure at different frequencies, take measurements at different points, and that will give you the resonance or oscillation or vibration modes of that mechanical structure, right? And based on that information, we can uh, refine the design of the structure or put some damping mechanism in the system, and that is how we eliminate or damp this oscillation mode. So we need similar tools in electrical engineering, in electrical power engineering, and that is where the impedance-based stability analysis comes in. This is an emerging area. Initially, the impedance-based stability analysis was introduced, I think, way back in 90s by Professor Middlebrook, and then over the last 10 years, it has gained more attention because of this more stability issues that come with renewables. So, what you see on your screen is the most simple form of impedance-based stability analysis method. If you have an inverter-based resource, which can be wind power plant, PV power plant, battery storage plant, HVDC converter, when you connect it with the grid, you want to understand if this inverter-based resource will work stably with the grid or not. So what we can do is we can uh, represent the inverter-based resource by a Norton equivalent circuit, basically a current source in parallel with the equivalent impedance of the inverter-based resource, or IBR. And grid we can represent by a Thevenin equivalent circuit with a voltage source in series with the grid impedance. And these are small signal impedance responses. They are basically transfer functions, so they are not just at the fundamental frequency 50 or 60 hertz. They are at a full frequency range or a broadband. And if I apply simple KCL and KVL to this equation, the relationship between voltages and currents in this diagram can be represented as a negative feedback loop on the right. And we have studied in control theory that if there is a negative feedback loop, we can use Nyquist plot or Bode plots of loop gain to understand stability of that uh, feedback loop. So we can, the loop gain here is the ratio of the loop gain is ZZ by ZI. So basically ratio of grid impedance to the inverter or IBR impedance. And we can apply various tools to do stability analysis from linear analysis. Uh, to simply use responses of impedance and inverter to do stability analysis, we have to make two fundamental assumptions. The one is that the IBR is stable without the grid, and the second is grid is stable without the IBR, or basically IBR and grid are separately stable. The reason to make this assumption is because when you apply Nyquist plot, you just want to look at the encirclements of critical point to see if the system is unstable or stable. If you don't make these assumptions, then there might be some hidden unstable poles in the IBR or the grid, which will, in a way, you will have to account for. So these are the two fundamental assumptions or fundamental premise for applying impedance-based stability analysis method. And these are very practical assumptions, because if we say that the IBR is stable without the grid, what I'm really saying is that the IBR will be stable when it operates with an ideal grid, an ideal voltage source. And a vendor is going to design a plant which is stable, at least will be stable with an ideal grid, which or with a strong grid. The other assumption is that the grid is stable without the IBR. And of course, when we are connecting a new IBR to the grid, we can assume that the grid is stable. So these two assumptions are not limiting, but they are, we have to keep in mind whenever we scale this type of impedance-based stability analysis to larger systems. So that criteria has been applied very successfully to many power systems. Like it is used by HVDC vendors. They design HVDC converters to make sure that their HVDC substation or converter is not going to interact or create oscillation modes with the grid on the AC side. Uh, it is used by wind power plants developer, by also many utilities like ERCOT in US, for example, to make sure that there are no subsynchronous resonance modes that are going to be formed when you connect a new wind power plant. So the question is, how do we scale it for larger systems? When we see these oscillations in a big grid where you see oscillations are appearing at terminals of 20 or 30 or 100 different IBR resources, and you can't really divide the problem like one IBR versus grid, because now the problem is all over the network where many IBRs are participating in that oscillation mode. So how do you scale that approach? And one way is basically assume that we remove all IBRs from the network, so isolate all IBRs from the network, so that only passives remain in the network, like transmission line, transformer, uh, filters. Basically, no active device remains in the network. And then we can assume that the network is stable, or basically, in a small sense, it doesn't have poles in the right half, if you understand control theory. So the network will be stable without all IBRs. And then we assume that all these IBRs are designed to remain stable when they connect with an ideal grid. So again, the usual approach that people have been using to scale the impedance-based stability analysis is to assume that all IBRs are stable individually when they connect to an ideal grid, and the grid is stable when you remove all the IBRs. So in this case, now you will have to look at the impedance of each IBR to do stability analysis, as well as of the network, looking from all these points of interconnection. So for example, in this diagram, I'm showing four IBRs, right? One PV plant, wind plant, one storage, and one feeder with several DERs. So if I want to do stability analysis of this power system using the usual approach, the I need an impedance response of all of these four IBRs, so four impedance scans, as well as of the network, looking from all the four ports. So if I look at the network from four different ports, the impedance matrix will be 4 cross 4, basically 16 elements. And as a power system engineers, we know that any three-phase port or three-phase network, its impedance is actually not one-dimensional, it is two-dimensional. If we define it in dq, then d and q are going to be two axes, so you have to consider the full dq matrix with four elements. If you use positive sequence, negative sequence, we still need to consider coupling. If you use phasor domain, where we consider magnitude and phase of a quantity, there also you have to consider coupling between magnitude and phase. But my point is that from each port, the impedance will be 2 cross 2. So for this network, the impedance will be actually, instead of 4 by 4, it will be 8 by 8. So 64 different transfer functions that you will need. And for each of these four IBRs, you will need a 2 cross 2 or 4 impedance scans. So basically, total uh, 4 by into 16. So basically, 16 transfer functions to define IBR response, 64 transfer functions to define network impedance response. First, and this is very challenging. So it is possible to scale the current approach of impedance-based stability analysis in theory, but it is not practical because you need a lot of impedance scans, and so that's why it is not scalable. And also, when you see the systemoid oscillations that I showed you earlier, uh, if you are a network operator, you want to understand uh, not all like you don't want to understand what all IBRs are doing in that oscillation mode. Probably you want to look at only three or four big plants to see what they are doing, whether they are contributing positively to the damping or negatively, so that you can take some remedial actions. Because your objective is that the whole system remains stable, not to like see all do analysis at all IBRs. If you are a vendor, let's say if you are a developer or owner of a wind power plant, then you want to just look at what your wind plant is doing in any oscillation event, so that a network operator doesn't curtail you or penalize you for any oscillations. So you just want to understand whether your plant is a positive contributor to an oscillation mode or a negative contributor. So my point is that we don't need to perform analysis at all IBRs in the system. Just for 4 IBR example that I'm showing, we are talking about 64 to 100 transfer function scans, that to at one operation point. So for a practical system, this approach is not scalable. So what do we do? How do we scale the impedance-based method to perform stability analysis? So again, the usual approach is we ask question: Will the connection of all IBRs to this system make it unstable? Basically, here if this cartoon you can think as standing on hill as a stable system, and the question we are asking is, if we connect all these IBRs, will that it will fall down the cliff or the system will become unstable? So here we need to do the scan of IBR, each IBR, as well as of the system, looking from each IBR. We take a reversed approach. So what we do is that we assume that the system is stable with all the IBRs, and we ask a question: will the removal of this particular IBR make system unstable? So in this case, if I'm focusing on this IBR n, I need impedance scan of only that IBR and the rest of the system, looking from that port. So I need only uh, two transfer functions, or if I'm considering the second order impedance matrix, then 4 for IBR and 4 for uh, the network. So only 8 transfer functions to understand what this IBR is doing in the stability. So this is a very high level explanation of what is this reversed impedance-based stability criterion. To implement that, we have developed a software tool where this is the graphical user interface of that software tool. It is built on to work with PSCAD model. So if you have a system model in PSCAD with all the wind plants and PV plants, all IBRs, and if you see oscillations, the this tool can help you understand what each IBR is doing in the oscillation modes. Or uh, for example, if I start with this PV plant, if I want to see what this PV plant is doing in that oscillation mode, I'll insert this yellow box, which is part of the impedance scan tool. We call it GIST, or grid impedance scan tool. So, and by interfacing with this GUI, this software will scan the impedance response of a PV plant and the network without breaking the system, without isolating the system. So I don't have to do a separate scan of PV plant versus the grid. This yellow box will basically look at both PV plant and the grid by essentially injecting some perturbations like a small voltage source in series. So if you go inside this yellow box, there are like three-phase voltage source in series, which, and you change the frequency of that voltage source, it is injecting disturbances or perturbations at different frequency. We measure currents going through this block, and that helps us derive the impedance at different frequency for PV plant as well as the rest of the grid. So we scan IBR and network impedance, we perform stability analysis. So that is how I get what this particular IBR is doing in the oscillation mode. Now I can repeat the process at other IBRs if I want to see what other IBRs doing in an oscillation mode. So let's start with an example. So here I have a power system with very large amount of penetration of inverter-based resources. It's a 14-bus system. It has one synchronous generator and 5 inverter-based resources. Some are grid following, some are grid forming. And I want to understand the stability of this power system with all the IBRs. So I select one particular IBR, inject this yellow box in PSCAD model. This graphical user interface will start scanning of the impedance of this IBR as well as the network that it sees on its terminal. The perturbation frequency, the recording length, the magnitude of perturbation, they all are automatically selected. There's a lot of signal processing involved in how do you post-process the scan data. Like if you know the impedance of a three-phase power system, it has a reference frame. Like for example, a DQ impedance, you have to synchronize the grid voltage with D axis. Similarly, there are reference frame for sequence impedance or phasor impedance. So this tool will automatically do the post-processing, synchronize the reference frame. It will optimize the window for Fft analysis, and it will minimize leakage errors and will give you basically a more accurate impedance scan. So that is the trick. How do you get impedance scans which are accurate? And it outputs impedance both in DQ and the sequence domain. We can apply this tool to a very large power system also, like Eastern Interconnection of US, where the model is not in PSCAD, but the model is in PSSC or positive sequence simulation tool. So we can use basically, we can combine the strength of co-simulation between EMT and phasor, or between PSCAD and PSSC, and impedance scan. So here you see a large power system is modeled in PSSC. A small part of it is modeled in PSCAD. And if I connect a wind power plant or PV plant in this PSCAD, I can insert this impedance scan tool at that point to try to understand stability impact of that plant. So to give you an example, in US, we are planning to integrate a lot of offshore wind power plants in the Atlantic region. Now, if we want to study the impact of all this offshore wind generation on power system stability, we'll have to model the offshore generation or offshore grid in EMT domain or electromagnetic transient domain using PSCAD, because the power electronics devices, their dynamics, it cannot be captured by positive sequence tools like a PSSC or PSLF. So we model the onshore grid in PSSC, the offshore grid, which includes offshore wind power plants and HVDC and HVAC transmission lines in PSCAD, couple them together through co-simulation tools, and then use this impedance scan tool to understand stability impact of all the offshore wind generation. So going back to the uh, system that I showed that we are going to analyze today using this tool. So this is a 14-bus system with two grid following IBRs, three grid forming IBRs, and one synchronous generator. Uh, when we simulated this system, we saw that there are some oscillations. These are the power output of all the generators in this system. And you can see that there's a 2.5 hertz oscillation mode. It's not like that some inverters are oscillating in phase and others are out of phase and they're like oscillating against one or against the another. The phase is all over the place, right? So this is indeed a very complex oscillation mode. Now the question is there a way that I can identify the frequency and damping of this mode without really waiting for this oscillation to happen? What is the impact and participation of IBRs in this mode? Like which of these are positive contributors or negative contributors? If you have heard about grid forming capacity, like can I use this tool to understand how much grid forming capacity is required for stable operation of this particular power system without synchronous generators or with very few synchronous generators? So to answer these three questions, we start with an impedance scan we select one of the IBR, insert this block and scan the impedance of IBR and the network. So here is a scan at one IBR, grid forming IBR at bus 6. So this is how and these are basically sequence impedance. It's a positive sequence, negative sequence, and coupling between them. So that's why you see there are four transfer functions: YPP, YPN, YNN, YNP. You can do this in DQ also. So in that case, you'll have YDD, YDQ, YQD, and YQQ. So this is the network or admittance of network that this grid forming IBR at bus 6 sees at its terminals. And this is the admittance of that IBR itself. In a way, the impedance scan tool or impedance-based analysis, it decouples the dynamics of IBR from the network, because now you are seeing the network admittance without this IBR, which is there at the terminal of IBR. And you are also seeing what is the IBR admittance. So it gives you basically dynamics of network without the IBR and then IBR without the network. And you can use this information to understand how IBR is impacting different oscillation modes of this power system. So for that, we plot the magnitude response of modal impedances. So modal impedance, this plot on your top left, that basically derived from the impedance scan that I just showed in the previous screen. So everything is measurement based. We are not using models. As I said, the main challenge with inverter-based resources is models. We can have a simulation models which uses real C or software code of wind and PV inverters, but we can't get real simple equation-based models to derive eigenvalues or perform state space analysis. So here everything is based on measurement or impedance scan. So from modal impedance analysis, we can find out what is the resonance frequency with or without IBR. For example, with IBR, which are this asterisks, we see it is 2.5 hertz, and if without the IBR, it is 2.3 hertz. We can also find out what is the magnitude of damping depending on how peaking this modal impedance responses are. So with IBR, we see 13.3%, and without IBR, we see 5.9%. But this modal responses will only tell you the magnitude of damping. It will not tell you whether the damping is negative or positive. So for that, we use a Nyquist plot. The simple criteria is that with IBR, we know system is stable because we started with a stable system. We want to analyze what happens if we remove this IBR. So if we remove this IBR, if this Nyquist plot is encircling this critical point, -1, in anti-clockwise direction, then the system is unstable without the IBR. In that case, the damping is negative without the IBR. So now we know what is the frequency of a mode and damping without IBR and with IBR. The differences will tell us what this particular IBR is doing. So this particular IBR is adding around 19% of damping to the system. So the damping with IBR is 13.3%, and out of that 19% is added by this IBR. So if I remove this IBR, I'm going to lose the system stability. We do that at other grid forming IBRs or grid following IBRs. For example, this particular grid following IBR, it has a higher damping without the IBR, the system, whereas with IBR, the damping is low. So uh, from that, we can find out that this is a negative contributor to system oscillation modes. And this is the final result we get, basically how each of the IBR is impacting the oscillation frequency or the oscillation frequency of oscillation mode, as well as its damping. Now, once you have this system, this information, you can tune controls at specific IBRs to improve system damping and make sure that you will not have any underdamped or undamped oscillation modes in the system, and make sure that the system remains stable in a small signal sense as you go for higher penetration. This can also tell you how much grid forming capacity you require. For example, for specific control design, we see here grid forming are providing higher damping. So if you reduce or eliminate any of this grid forming IBRs, the system will become less and less stable. So through this simulation study, you can also quantify how much grid forming capacity do you require to make sure there are enough stability margins. So switching gears a little, this tool that I just described, the software tool, it actually came as a byproduct of the hardware impedance measurement system that we have developed at NREL. So I think this slide shows in a more clear way what I mean by impedances, if you haven't yet got clarity on that. So to get the impedance response, if this is the grid simulator that we have at NREL, a 7 megawatt grid simulator, which generates three-phase voltages, and we can control its voltages in any manner we like, inject perturbations, create voltage steps, phase jumps, create fault events. So it's a fully controllable a voltage source. And let's say if I want to measure the impedance of this wind turbine nacelle, which is in our laboratory, what I will do is that on top of the fundamental voltages at 60 hertz in US, we inject small perturbations that you see on these voltages, and we see what will be the response of this device in the current. So it will also have fundamental component based on the active and reactive power output at its terminal, but it will also respond to this perturbation that we are injecting in voltages. And a transfer function, basically gain, the magnitude gain between voltage perturbation and current perturbation, and the phase difference will give me the impedance at that frequency. Now I do the scan from low frequency at NREL. We do from a fraction of hertz to a couple of kilohertz, or 2 or 3 kilohertz, and this is what we get on the right side. Basically, what you see is positive sequence impedance response of a 4 megawatt wind turbine under testing, and we need to consider frequency coupling. Here I'm just showing a positive sequence, but if you want to do stability analysis at low frequency, you have to consider coupling between positive and negative sequence. But this is how you basically get a transfer function between voltage and current. This is a cool graphic showing really what is happening during the scan. So on top left, we have voltages that we are imposing on the 4 megawatt turbine terminals with perturbations. Top right is the Fft analysis. So in addition to this big line, which represents the fundamental component at 60 hertz, we are seeing this perturbation which is moving as we are changing the frequency of perturbation. This is accelerated, so we don't change perturbation frequency this fast, by the way. So that is the Fft analysis. The bottom left is the current output from 4 megawatt turbine with perturbations. and then bottom right is basically Fft analysis of current. So the gain from voltage and current will give us impedance. So this is how the scan is performed, either in the impedance measurement system that I talked about, or the software tool, PSCAD-based software tool. Here are some real measurements of impedance response of grid forming versus grid following IBRs. So there's a 2.2 MVA battery inverter at NREL. You can operate that in both grid following versus grid forming mode. And you see the positive sequence impedance in both these modes. This is for 2 megawatt PV inverter, again in both modes, and this is 2.5 megawatt type 3 turbine. There are a couple of things I would like to highlight here. So around the fundamental frequency, the device will have a lower impedance in grid forming compared to grid following, as you can see here or in this case. And the reason is, in a grid forming operation mode, the device is trying to act as a voltage source similar to synchronous generator. And we know that an ideal voltage source will have a zero impedance. Whereas in grid following mode, the device is acting as a current source, or it is controlled as a current source. And an ideal current source has infinite impedance. So that's why in the grid forming mode, the impedance magnitude will be lower. So this is one way to uh, understand whether that device is operating as a grid forming or grid following. We can quantify the grid forming behavior this way. The the other interesting thing is that for grid forming, usually the device will have a better damping. For example, uh, this green box, which basically highlights range of plus or minus 90 degree in the phase of impedance. You see for grid forming, the phase remains pretty much within this green box. So the phase of impedance doesn't go higher than plus 90 or lower than minus 90. What it means is that the impedance will always have a positive real part, or that means impedance will always have a positive resistance in a grid forming mode. Same as for the PV inverter and for the wind turbine. That in grid forming mode, most for most frequencies, uh, the IBR will have a phase, impedance phase will be within plus or minus 90 degree, or it will have a positive damping. So I'm not saying that grid forming will never have a negative damping or a negative resistance behavior, but at most frequencies it will be have a positive damping, and it will help in the system damping or system stability. The same as we saw even for the 14 bus system example in PSCAD. So with that, I would like to summarize the impedance scan tools are critical to understand small signal stability of IBR grids. I started working on these tools back in 2012 when the most control interactions were local in nature. As I said, in 2014, there was interaction between an offshore wind plant and HVDC. Uh, so the impedance scan tools became very popular within the industry, both system operators as well as device manufacturers, to understand control interactions. And now, as we are going with seeing power systems with operate with even higher and higher IBRs, we see system-wide control interactions or system-wide oscillations. So they are becoming more critical, and this is still a very new field. As I said, most developments have happened in last 10 or 12 years in this field. So still we are figuring out how to apply this frequency scan tools to understand system stability. The main applications are identify underdamped or unstable oscillation modes in the system, estimate the role of different IBRs, identify which IBRs are creating those oscillations or helping damp those oscillations, where we should implement damping, uh, how we can estimate inertia or impedance in a non-invasive manner, or basically in real time. So let me spend a few minutes on talking about the remaining problems in this area. So the first is how can you accelerate this impedance scan, because there is a big hurdle. If I have to perform impedance scan of one IBR at then if I'm doing at zero point 0.1 hertz, the FFT window should be at least 10 seconds longer, right? Because I want 0.1 hertz of resolution. And if you are talking about a very big system, like in Brazil or a big Eastern interconnection in US, or even a small regional power system in PSCAD, simulating for 10 seconds takes probably an hour, one or two, or more than a couple of hours actually sometimes. Now, if you have to do it at multiple frequencies, then just to perform one impedance scan, it can take a really long time. Uh, if you're doing it at low frequencies, like less than 1 hertz or less than 3 or 4 hertz, one a decent impedance scan takes around half a day. Uh, for high frequencies, it's easy because if the oscillation modes that I'm seeing are occurring at a couple hundred hertz, like 200 hertz, then I can have a really small FFT window, right? Like a fraction of a millisecond or a couple of few milliseconds. So for high frequency scans is easy, but the most oscillation modes that are going to be system wide, they are going to be low frequency. The reason being the high frequency modes, they don't travel farther in power system. So that's why the speed of impedance scan is a big challenge. Second is how we can parallelize this problem. Right now, as I said, like our tool uses the impedance scan at one IBR, but if I want to understand the stability impact of 5 IBRs at a time, what should be our approach? That will again reduce the time required to do this study. Uh, the third is accuracy, because you can do a very nice impedance scan for small simulation models, which is very stable. There are no noise. But when you get PSCAD models of from vendors, which are real code models, use real software codes, there's a lot of going to be jitter. If you see like a big power system model in PSCAD, even in steady state, you will not have like a really flat voltages and currents. There will be some noise in the system. So when you do impedance scan, you want to inject perturbation which is high enough so that your measurements are above the noise floor level, or basically you have a good signal to noise ratio. But at the same time, you don't want it to be too high to accept non-linearities in the system, because this is at the end a small signal impedance analysis or small signal stability. So what should be the level of perturbation at different frequencies? It doesn't have to be constant. For example, if I'm scanning the impedance of a type 3 wind turbine, which has an induction generator, at low frequency, it's mainly inductive. The impedance is mainly inductive because it's induction generator. So you will just see inductance of the generator. Now, if I keep the voltage perturbation high even at low frequency, the inductance will have very low impedance at low frequency and will result in a lot of current. So you also need to control uh, the perturbation, or uh, smartly choose perturbation, not just for one impedance scan but also at different frequency, like how intelligently you select this perturbation level. So these are all open questions, and I think it's a very exciting and new area of research. We are seeing every few months we are seeing some oscillation, like here about some oscillation event at one or the other place in world, and we power system engineers don't have really refined tools as mechanical engineers who do this vibration analysis for several decades now. So there's, I think there's a lot of interest in this. So I'll be happy to answer any questions that you have, either specific to this presentation or where this field is going. So with that, we are also at the time 2:45. So thank you for your interest and attendance in this. And yeah, just acknowledge all my colleagues who have been working on this tool. So of course, it's not just my work. We have worked together to developing the impedance measurement system as well as the impedance control. So just acknowledging their contribution. Thank you.
So thank you very much, Dr. Shahil, for the presentation. I definitely learned a lot from it, and I have some questions regarding it actually in technical terms. Um,
Sure.
yeah. So my first question here, is that, have you observed this phenomena that the harmonics at low frequencies in just weak grids, or you even observe those in strong grids as well with high SR, high SCR?
Usually, we have not seen them in strong grids. They are usually at places where we don't have a lot of synchronous generators. Uh, it's only only during weak grid conditions they are more pronounced. But then I don't want to say that the V grid is the only scenario where you will have these oscillations, because, for example, if you talk about offshore wind power plants where an HVDC converter is connecting with offshore wind plant, there's no grid, right? That's like one is offshore converter and then wind plant. So in a fully power electronic system, also you can see these oscillations. Electric traction networks where there is again no grid. There's uh, basically a high density of power electronics. So in the existing power systems where we have this IBR penetration low, not really high, they mainly occur during weak grid conditions. But as we go towards more fully power electronics system, the weak grid concept doesn't work, right? Because what do you mean by weak grid? Is it just impedance at the fundamental frequency that it should be an ideal voltage source, or at other frequency? We use short circuit ratio, which is basically what is the fault current contribution at different nodes. Uh, but again, that is a good way to get some idea about whether the grid is strong or not, but not a perfect metric
Yeah, yeah.
to quantify grid strength.
Yeah, it is the measurement that we have, to measure the grid to be strong or
Yeah.
not. So that's what you have. But I do think your answer was very good. Professor Watanabe is also here with us, but if he let me, I'm gonna ask another question here, very fast. Two questions actually. From the phenomena that you observed, like the low frequency resonances, could you say these phenomena are strictly related to the control interactions between the voltage source converters?
So usually, I think as an industry, we started like whenever the power electronics is involved, control interaction is a term that is used because most of the dynamics of power electronics or voltage source converters they are governed by control. So usually it is control interactions, but then there are interactions where it will be between the power electronics converter, that's an HVDC station, and the synchronous generator, where mechanical dynamics are involved, right? Like for low frequency interactions, when subsynchronous, like we qualify subsynchronous torsional interaction as different from subsynchronous control interaction. But sometimes what might happen is that the controls of an HVDC station will interact with the torsional dynamics of a generator, which is there in close proximity. And there you can't really say that it's control interactions or torsional. It's just basically small signal dynamics. So
Got it.
uh, I hope that answers your question.
They definitely did. Thank you. Do you wanna make some comments, Watanabe, about the questions that I
Just one, I have some, but just to start, Shahil, you said that weak system is a problem, or weak grid. In the case of offshore wind, normally you do not have grid there. So the rectifier, or in the case of HVDC, has to be as a grid forming, I suppose. And in this case, is it a strong grid, or normally it's 1-to-1, no?
So it is. The grid strength is a good metric to see whether there's a risk of control interaction, because most inverter-based resources like wind turbines or PV inverters, the vendors they design it for particular grid strength, right? So it's a good metric to quantify risk of control interactions. But as you said, like in terms of offshore HVDC, there is no grid. It's formed by the grid forming inverter. So in that case, it's not really this grid strength which is creating this control interactions. It's simply like you see the impedance of HVDC, impedance of the offshore wind plant, compare them side by side, and see where they are interacting, like where they are intersecting. If if they're intersecting at a one particular frequency, let's say 157 hertz randomly, you look at the phase margin or stability margin at that point, and if it is low, you'll have instability. So yeah, as you said, like it's at that point we can't really say that the grid strength is creating these issues. It's just a good way for AC networks, or like our conventional power system, to quantify the risk of these issues. But then as we move towards more power electronics based systems like HVDC, where you have no synchronous generator, then it's not really grid strength. It's just about how these controls are going to work together, because we have designed them to work well in isolation. But when you connect all these hundreds of controllers with each other in a way, whether they will fight at certain frequencies or not. So at the end of the day, that's what it is.
So, Professor Watanabe, are you satisfied with that answer? I do have a lot of other questions regarding it.
Just one comment. You
Okay.
said that the mechanical engineers, people that they work with this for a long time. But I think there's a difference, because there it's like a single phase system, isn't it? In our case, this three-phase is something that they do not have. And is it something that makes
I'm not criticizing electrical engineers that why they have not been working on this thing. You are right, the system is simple, or the structure is simple, right? You can bring the structure in one laboratory and test it, whereas our power system is spread like hundreds to thousands of miles. And the reason we didn't start focus too much on this aspect is because we had really good models like synchronous generators, very standardized models, the controls, exciter, governor, PSS, power system stabilizer. Everything is standardized and open, so you can define it with through good mathematical models. There are industrial tools which can do eigenvalue analysis, find out what are the oscillation modes. So we didn't do it because we didn't have a requirement. We had good models of our power system, but with all these IBRs, we are not getting good analytical or equation based models. You can't, like if you look at a typical wind turbine, the its software code will be like 2 to 3,000 lines of C code. In fact, probably more. But based on what I know, it's like that is a C code will have like 3,000 lines of C code. Then how do you convert that into few 5 or 6 differential equations? Because there are so many non-linearities, control mode changes are involved, and that's why now these tools are becoming getting more attention. And I'm sure that just as mechanical engineers will also develop our software tools will suit our needs. And you're right, it's more complex for power systems because it's a three-phase. We have to worry about coupling between different positive sequence, negative sequence, DQ. It's not like just a single measurement like a displacement at one point, right? So yeah, it's more complicated for power systems for sure.
Yeah, they don't have negative sequence.
Yeah, they don't have negative sequence.
Yeah.
But yeah, the questions that I do have are questions after the slide 20 that you presented, considering the perturbation that you did, the disturbance that you did on the voltage of the grid, to see how is the answer of the converter in terms of currents. You know, if you put a voltage perturbation or a disturb in a specific frequency, you're gonna have that particular harmonic in the currents, which depends, of course, on the impedance seen by that particular IBR. Correct. My question.
You're talking about this slide?
I can't see because it's not being shared at the moment.
Okay.
But it's on slide 20.
Oh, I thought it is. I see it is being shared in my screen.
It's probably because the okay, now I can see it. Yeah, that one. So basically, if you do have a voltage disturbed in a particular frequency, you're gonna have a particular current by that inverter at that frequency, right? And what defines that, or the magnitude of that current harmonic, is the impedance seen by that particular in this case, wind turbine. My question is, what is the solution for that particular problem? I do think it is a control solution, but what exactly in terms of control should you implement to mitigate this?
Yeah, so that's a good question. Probably you're talking about how can we shape this impedance response at different frequencies to make sure that all the oscillation modes in the system are sufficiently damped. So it's a combination of control and hardware solution. Like for example, the control bandwidths for most wind turbines or PV inverters, they are limited to few hundred hertz, like up to 200 to 300 hertz, because they operate at switching frequency of couple of kilohertz. So that's why their control bandwidth should be less than couple hundred hertz. So within that bandwidth, you can tune your controls to shape impedance. But if you have a resonance which is occurring at a frequencies which are outside of control bandwidths, you can't really change impedance by control tuning. So in that case, you'll have to have some additional dampers or filters in the system to damp it. So that is one answer, that what control can do is limited by the bandwidth. The second is what you should do in the controls. So it depends on, for example, the current control of most of these inverters, it's a few hundred hertz. So if your oscillation frequency is in that range, then you will tune current control. If it's like a PLL, then for PLL also you can use control tuning in that frequency range. If oscillations are very low frequency, around 20 hertz, most likely you'll have to tune controls of DC bus voltage control, or basically voltage control. If the oscillation frequency or resonance appears even at even lower frequencies, like a couple of hertz, then you should be focusing on active reactive power control, those type of slow control functions. So which control to select, that depends on what is the frequency range. And of course, as I said, that you can do control tuning to dump this oscillation modes only up to certain extent, depending on your control bandwidths.
Yeah, that was a very good answer. I couldn't be happier with that answer. Very, very good to know. The other question that I have, which is in the same topic, is what is the effect of disturbing the grid in these low frequencies to characterize the behavior of the converter? Because it basically did in the other slides, frequency disturbs in very low frequencies, right? Very near one hertz, or maybe even lower, I think. What is the effect of doing that in a major system, in a system as a whole, for example?
So this is a small signal scan. So we are disturbing, like injecting the disturbance at a really small scale. So we are not like dropping a big 100 megawatt of load, or injecting disturbance which are really large. If you talk about the actual measurements that we do at NREL, our grid simulator is in a way isolates the grid from all these experiments. And in the PSCAD software tool, that where I use a yellow box between an IBR and the grid, the perturbations are small. As I said, like we want to keep it small enough so that they don't excite any non-linearities. So that way they are not going to basically create any instabilities.
Do you have a number for that particular small? Because I've been getting a lot of questions regarding that topic lately.
Usually,
yeah, okay.
Usually you would like to keep it both your current perturbation and voltage perturbation at less than 5%. So it might, as I was giving the example of induction generator or type 3 wind turbine, that at low frequency the impedance is inductive. So even a very small, like a 0.1% of perturbation will excite probably 20% of current. So in that case, you need perturbation to be even small. So to give you a rough number, you want to ensure that both voltage and current perturbations are smaller than 5%. Now, to meet that condition, sometimes it might happen that your voltage perturbation should be like a 0.5%, so that your current perturbation stays within 5%. So you want to make sure that this both are around, at least one of them is around 5%. So that way you are still in a small signal regime. You are not exciting nonlinearities, but at the same time, it is like at least one of them is high enough that it's above the noise floor.
Yeah, that was very very informative. Thank you very much for your answers. Watanabe, if you do have a lot of other questions that you want to ask our guests, feel free.
I think we are just in time, but this frequency impedance scan tool basically is in PSCAD. Is there any try to make it experimental?
That's a great question, and we're exploring that. Basically, can we look at the basically can we insert some perturbation devices at different points in the grid and take measurements at different nodes in the network and see what is happening. So that we are exploring, but it's difficult because having a real perturbation devices in the grid, not in PSCAD, it's like a very expensive equipment, and then doing all the scans, it's difficult. I was trying to see if I have questions in chat, but looks like it's in Portuguese. So
yeah, we didn't quite get the answers in the chat. I was reading here to see if we had any other particulars, but I do think the questions that I've raised and Watanabe raised are also within the questions that we gather from our research groups. So I think that was pretty enlightening.
yeah, I'm happy to help, and yeah, please let me know if you get any more questions and send it my way to my email, and I'll be happy to respond to that.
Yeah, again, thank you very much for your time. We were very pleased to have you here with us. Very enlightening presentation, and I think we can end our presentation here. Thank you very much, all of you, for watching us at the moment, and I think we can end here.
Thank you.
Yeah,
Thanks.
thank you. Thank
Bye.
you. I think I learned a little bit more, but still I have to study this subject.
Yeah, I think we all are learning. So thank you so much.
Exactly.
Thanks for the opportunity. Bye.
Thank you. Bye.